This video is part 2 in the series on gears. Let's first review the operation of the simple spur gear. The motor tells us that this is the driver gear. What is the direction of rotation of the driven gear? We see that it's counterclockwise, the opposite of the driver as expected. Recall how we calculated the gear ratio. It's the number of teeth on the driven, 16, divided by the number on the driver, 12. So that is 16 to 12 or 4 to 3, and can be written as 4 over 3. But remember that when we talk about rotations and not number of teeth, then the first number refers to the driver gear's rotations and the second number to the driven gear's rotations. So in this case, we can say that the driver rotates 4 times for every 3 rotations of the driven gear. Recall also that the larger driven gear means that this is a gearing down system, which means the driven gear is moving more slowly than the driver. This is also called gear reduction. The driver is also called the input, and the driven the output. Now suppose there's an application that requires the output to turn in the same direction as the input. How can this be achieved? The answer is to insert another gear in between the driver and the driven. This gear is called an idler and makes this a 3-gear gear train. Now let's determine the driver by a motor again, and this time observe the direction of rotation of the driven gear or the output. So you see how the main function of an idler is to cause the driven to rotate in the same direction as the driver. And interestingly, the size of the idler has no effect on this change in direction. Now let's see if the gear ratio is affected. The ratio between the first 2 gears is 10 to 12 or 5 to 6. The ratio between the second 2 gears is 16 to 10 or 8 to 5. We now multiply the 2 ratios to get the final ratio, which is 4 to 3, unchanged from the original 2 gears. So the idler gear, no matter its size, does not affect the overall gear ratio, only the direction of the output. If the direction of the output did not matter, the idler gear would be unnecessary and also undesirable, because more gears means more friction, which reduces power. So this is one factor that engineers want to minimize for better efficiency. Idlers are also used to connect crankshafts to each other in cars. They are used in lathes. They are better than belt drives or chain drives in transmitting power, and so are used in some high-end cars. Now, suppose we wanted a larger gear ratio. We could combine a small 8-tooth gear with a large 32-tooth gear to get this ratio of 4 to 1. There are even larger ones that can be used with 48 or even 120 teeth. But this becomes cumbersome, and engineers often have space limitations for their applications. A better way to get large gear ratios is to use smaller gears that are teamed up in pairs. For example, here's a gear pair of 8 and 12 teeth, whose ratio is 3 to 2. Here is a second pair with 8 and 24 teeth, giving a ratio of 3 to 1. In each case, the smaller gear is the driver. If we lock the second pair onto the first like this, it creates a new gear train. The middle axle now has a 12-tooth driven gear and an 8-tooth driver gear. This type of gear train, where one or more axles has both a driven gear and a driver gear, is called a compound gear train. What is the gear ratio for this compound gear train? We multiply the ratios of the individual gear pairs. So 3 over 2 times 3 over 1 equals 9 over 2. This is also understood as 4.5 to 1. This means that for every 4.5 revolutions or turns of the input or driver gear, there is 1 turn of the output or driven gear. We have achieved a slightly higher gear ratio this way without using the large 32-tooth gear. Let's examine this compound gear train and calculate its gear ratio. The first gear pair ratio is 12 teeth divided by 8 teeth, which is 3:2. The second pair is the first gray gear, 32 teeth, being driven by the blue gear with 8 teeth. This gives the ratio 32/8, which equals 4:1. The third pair is the next gray gear, which is the driven gear, 32 teeth, divided by the small blue driver on the second axle, 8 teeth. This ratio is also 4:1. So the overall gear ratio is 3/2 times 4/1 times 4/1, which is 48/2, which simplifies to 24:1. This gives a slow output speed. The output turns once, while the first driver turns 24 times, but provides a 24-fold increase in torque or twisting force available for a heavy lift. Gearbox. Finally, gears inside a box are called gearboxes. Here is an example of a single gearbox as a kit from Pololu in Australia. They can be very complicated. Here's a double gearbox, and this is a gearbox in a car transmission. And finally, here's a giant gearbox that is undergoing an inspection. This ends the video on idler and compound gears.